I'm waiting. I see more people joining us slowly. Maybe it's a lot of people thought this was at 11:15 again. And I apologize for those people who are just joining us now. It's okay to be late to class. But, all right, any questions? Any questions? I'm not seeing anyone jumping in with questions. So I could, one thing that I could do real quick is just take a look, and we could talk about a couple of the questions really quick. Good morning, Saad. Welcome. David, can you explain the relationship between confidence and significance again? Absolutely, I can do that. I'll do that really quick as best I can. So I'm going to go into Khan Academy mode. This is Mr. Zach being like Sal Khan, except more statistical and with his real hands, not some type of digital pen. All right, so when I posted the video trying to make a connection between the levels of confidence and the levels of significance, right? So when we make a confidence interval, let's take a step back. When we make a confidence interval, what is the purpose of a confidence interval? Someone tell me in the chat, why do we make confidence intervals? What are they for? What are we doing when we're doing this? Let's see, I'm being patient. If someone wants just to open their mic, they could try to explain that way too. That's up to you. Liam, I see guessing the mean with confidence. Kate, to estimate the parameter. You are both correct, right? Something like that. You are right. So yeah, in a confidence interval, we're trying to estimate some parameter, right? So the parameter, right, frequently might be like a mean, mu, or it could be a proportion, p. And I point out these two because these are pretty much the only parameters that we're going to actually be estimating in our class. There isn't any reason why we couldn't come up with a confidence interval for sigma squared, though that's not something we actually do in AP Stat. We could try to come up with, remember how we were even doing in the German tanks problem, we were thinking about trying to figure out what the max was of a population based on some sample data. So all of those things could be parameters that we're trying to estimate. So the idea is, though, that when we estimate it, we did it with some level of confidence, right? And the level of confidence was associated with, I don't know what, that looks like right skewed. That's a crazy normal curve. It makes me sad. But when we looked at a level of confidence, it was based on imagining about how far out we should go from, say, an unknown parameter. Say these are distributions of X bar. About how far would you have to go to get to a certain percentage of all the sample statistics you would probably encounter for that statistic, right? And so when the distribution was a normal distribution, then this would be some z-score here, some negative z-score over on this side, and whatever percent of how far out we had to go, how many standard deviations we had to go away from the mean would be associated with some level of confidence, say like 95%. Akira, follow me on TikTok. What the heck is that? All right. I'm not TikToking, so I don't know how that works. But anyways, I don't know if you want to follow Nakira or not. That's up to you. But so a certain z-score to go out to get to a certain percentage under the curve when you had some unknown mu. And the idea was that the total amount of variation away from the population mean you'd get in your sample means was based on the population standard deviation divided by root n. Say for if we were working with things that were normally distributed. All right, so that was that idea there. That now, when we're doing a significance test, we have our goal for a significance test is something different. Our goal for a significance test is not to estimate a parameter, but it's to evaluate a claim. Evaluate a claim about a parameter, right? And so these claims get turned into hypotheses where there's some null hypothesis that we're going to assume is true, and there's some alternative that we're going to try to prove is true, right? And what ends up happening is we evaluate a claim by seeing if the evidence in favor of the alternative is the evidence in favor of the alternative is actually significant, whether it would be very unlikely to occur by chance, assuming the null hypothesis is true. So the key here is that we would be looking at essentially the opposite of the percentage that we see in a confidence interval, right? Instead of focusing on the amount in the middle, we'd be focusing on the amount on the edges, right? And so say we had a two-tailed test, right? We have some claim about what mu is. Some claim about what mu is. And if we have set a particular level of significance, then what we'll say is anytime we get a sample statistic that's really, 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 really far away from our null hypothesis, then we'll call it significant. And how do we measure how far away it is? Well, whether or not it is so far away that the p-values gets to be below some particular number. So this area out here would be associated with the level of significance, which we call alpha. This, if it was corresponding, say, with a 95% interval, then the area on the outside here would be 2.5% on either side, for a total of alpha equals 0.05. Right? So the core idea is when we're estimating something with confidence, we're focusing on what percent of my X bars should be close to the mean. 95% of them should be within a distance that's this many standard deviations from the mean. In a significance test, there we go. I just saw, Evan, you were about to present there. You can present if you want. In a significance test, we're looking to find evidence that mu is not true. And so we're going to be trying to find things that are really, 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 really far away from the mean. The amount of variation in either case is going to be based on sigma over root n, at least if we were working with a mean and we knew the standard deviation of the population. But that's the key idea there. So in general, the level of significance will always be 1 minus the level of confidence if we were looking at two-tailed tests. Let's see. How is that, David? Let's see here. I'm looking at the chat here. Follow Mr. Zach on TTAC. Zach Attack AP Stat God. If there is a TikTok that says that, then you can let me know, because that's not mine. All right. So the reason why it's interesting to point out this confidence interval and the significance test and the connection between them is because sometimes we'll actually have a choice as to how we would end up carrying out a significance test. We sometimes will have a choice as to whether or not to do the significance test using a p-value or using a confidence interval. So if, say, you had the null hypothesis was that mu equals, I don't know, let's say the average score on a test is an 85, and the alternative was supposed to be that the average is not an 85, right? It's so funny how I write my numbers differently. That one was sort of like two circles. That was, I don't know, that's weird. I do weird stuff like that sometimes. But if we said mu is the true average on a test, right? Let's say instead of actually giving 1 million people a test, I gave, which is, say, the size of the population, I gave just some sample. Well, if I was to try to evaluate these hypotheses based on some sample data, right, I could have, say, a sample mean that said, say I sampled 36 folks, and let's say the mean of that sample ended up being something that's different from 85. How about 89, right? And let's say I knew on this test magically, somehow, gloriously, that the standard deviation of people's scores on this test is always going to be fixed at the value of 8, right? So I'm doing this just to simplify so that we can use a normal distribution. We don't have to worry about t-distributions yet. And we'll get into that next week. If I wanted to use this to evaluate these hypotheses, I would actually have a choice, right? I could make a confidence interval. Confidence interval. And if I was to make a confidence interval, I could check. I'd make an interval that's centered at 89. So remember, a confidence interval is a sample mean plus or minus, in this case, a z-score times the population standard deviation divided by root n. And this confidence interval would be centered at 89. And we'll see if we manage to capture H naught in there. So we could ask ourselves, is H naught in the confidence interval? That would be our question. And make that look like that. All right. So if we remake the confidence interval, we go to stat tests, and I could do a z interval because I'm working with a normal distribution when I know the population standard deviation. I could put that population standard deviation in as a 8. I can make the sample mean 89. I can make my sample size 36. I didn't give a level of confidence. What level of confidence do you guys want to use? Someone tell me. You give me a level of confidence. I don't even care. 93%. Saad, Liam, you guys are Aaron, 87% confidence. You know what? You guys are crazy with your levels of confidence. I'm going to go with and then Lynn 90, Liam a 0%. All right, here's my 0% confidence interval. Ready? All right, here you go. The 0% just for Liam, 0% level of confidence. Then my confidence interval would be 89 to 89. There you go. That's 0% confidence. Why? Because that would mean I had a X bar plus or minus the z-score for 0% times 8 divided by root 36. Now, of course, what's the z-score for 0%? That would be 0. So you've got X bar plus or minus 0 times 8 over root 36, which would just be X bar plus or minus 0. So boom, there you go. 89 to 89 would be your 0% confidence interval for you, Liam. But that is kind of worthless. No offense. All right, but let's pick one. Let's just do 95% because that's our standard. Lynn, you're really adamant on that 90. All right, Lynn, this is for you. We're going to do the 90%. All right. So let's say we did 90% confidence. Then we could, if I was to do this by hand, then this guy would become X bar, which is 89, plus or minus the z-score for 90% confidence. I got you, Lynn, is 1.645. Now I had that memorized, right? And hopefully you might as well right now. But that's the z-score for 90% confidence. And I also do this in calculator and show it. And that would be times the population standard deviation, 8, divided by the square root of my sample size, which is 36. And so that would be 89 plus or minus. I got my calculator. So I'm going to do this by hand first because that's how I'm rolling. 1.645 times 8 divided by square root of 36 is 6. So that would be 89 plus or minus 2.193. Repeating. Let's see here, Liam. That's fine, Liam. I'm not offended that if you have to go see what Harkness is up to, and that's cool. That's one of these things. I'm going to talk to Harkness too, and the other teachers as we get more conflicts like this, how to make sure we can set up a schedule that works better for everybody. So anyway, it's all good, man. But so if I had 89 plus or minus 2.93, that would be 89 plus 2.193 plus that. And then I also do 89 minus this guy. And so our confidence interval should have been 86.8 up to 91.2. And this is at 90% confidence. So cool. Now, if this was my result, would this cause me to reject or fail to reject the null hypothesis? Well, I would take a look, and my null hypothesis was that, and let me get a different color here. Let's get some blue. These are my thin markers. I'm still not thrilled about buying these thin markers. I'm kind of upset. But there, I've got my 85 as my null hypothesis, and I check, is 85 in this confidence interval? The answer is no, right? So if I was using a confidence interval to evaluate these hypotheses, I would say since mu equals 85, right, is not in the interval 86.8 to 91.2, I reject. It does not say since. Okay, Harry, here you go. Is that better? Still not much better, but there you go. Since mu equals 85 is not in the interval, I reject the null hypothesis, right? Yep, sorry, Nick here. We do reject because it's not in there. We're rejecting that it is 85, and we have evidence that it's not 85. How do we know that it's not 85? My 90% confidence interval estimated it to be between 86.8 and 91.2. I reject the null hypothesis. I would say I have significant evidence that mu is not equal to 85. Right? In this case, that, and you know what, I could even put this in words. Remember, mu, I said, was the true average on a test. And so, in fact, I could say, in place of that, let me use a different color. Let's say here, I got green here. Yesterday was St. Patrick's Day. I forgot to wish you guys a happy St. Patrick. I was wearing green yesterday and everything. The true average on the test is not equal to 85 is essentially what I conclude. And that would be me working entirely based on a confidence interval. Let's evaluate the same deal using a significance test, right? Now, let's think, what would be the appropriate level of significance that we actually used here? What was the level of significance? Well, because I did a confidence interval with 90% confidence, right? So I had 90% confidence, and it was a two-tailed test, right? Because I was just looking at not equals. Dominic's got it. The correct at 90% confidence, then this would have been an alpha equals 0.10. This would have been a 10% level of significance, right? Which means it's we're making it relatively easy to reject the null hypothesis because we're only going to have a confidence interval that's 90% wide. And we actually will have a pretty high boundary for what counts as an unusual p-value. So, all right, we did it with a confidence interval. Let's do the exact same thing now with a significance test. So I'm going to take another piece of paper, and I'm going to keep just the relevant key information here, and then and let's construct this thing. So option one was a confidence interval. Let's see, option two, let's do a significance test. And we'll do alpha equals 0.10. So we're consistent with the level of confidence we had used for this confidence interval. Okay, so for my significance test, in this case, in terms of the math that we're doing, we're going to first calculate a z-score, right? And this z-score, and I've kind of alluded to its name, but I didn't use it in the videos. This z-score is going to be called a test statistic, right? It's our testing statistic, and in this case, we're going to try to figure out what was the z-score for x bar, right? How far was x bar from the null hypothesis relative to the amount of variation that we would expect to assume, right? That we would expect to see in the sampling distribution. So what I would do is my test statistic z, and pink is a little light. Let me get a better color. Let's go for a darker red. Oh, baby, look at that guy. The z-score will be, all right, so my x bar minus whatever my hypothesis was about what mu is. And notice I'm actually going to put a little 0 there because this isn't necessarily the true mu. It's just what I'm hypothesizing mu to be, right? So let's say, and then I'm going to divide that by the formula for the amount of variation I'd expect to see, which would be sigma divided by the square root of n. So let's calculate this Jansky. I'm going to say I've got 89 here, 89 minus 85 divided by 8, which was my population standard deviation, right? And we'll divide that by the square root of 36, right? Let's see what we got as a z-score. I'll do 89 minus 85 divided by 8 divided by 6. Exactly 3. Holy shnikes. That's pretty crazy. It came out to exactly 3.0. It almost never happens. Crazy. All right. Is that cool? Now, this means that when I'm thinking about, there's a couple of things that I could do even prior to doing the math. One thing that would be interesting to take a look at is I agree, Ostap, that is some crazy stuff. One thing that's interesting to compare is this test statistic with the z-score that we actually use for 90% confidence, right? And if you think about it, before I even calculate the p-value, this will already give us one way of sort of seeing that we're going to end up rejecting. When we had a normal curve, all right, Harry, go have fun with Harkness, man. When we had a normal curve, you can, people who are leaving, I'm going to post this online. So if you want to watch the end of this, just watch the end of it. But in a normal curve, remember, standard normal, you go out 3 standard deviations from the mean. And we said that 1.645 was the z-score for 90% confidence, because if you go out 1.645 standard deviations from the mean and you shade it in, this guy would be 90% of the curve. And then these outer parts would be 10%. And so again, then you had to go out 1.645 either way from the mean. What we just saw is we got a test statistic of 3. And 3, where is 3 on here? Let me get another thin marker. 3 is, well, all the way out here. Actually, well, that's -3, excuse me. But 3 is right there. Boom. There's my sample mean. My sample mean's z-score. From the test statistic for my sample mean was all the way out here. Just seeing that alone is already pretty good reason to realize that I'm going to reject the null hypothesis, because I have to go way beyond what would be considered the boundaries for a 90% interval, right? So let's go ahead and calculate the p-value, and we'll certainly see that that we'll get a p-value that's less than 10%. Okay, so to calculate the p-value, then what we'll do is we're actually going to find the probability that we'll have a z greater than 3.00 union with the probability that a z is less than -3.00. Now, why am I doing both? And that's because we had a what? Someone tell me, why am I looking at 2 directions instead of just the Anthony said it, David said it. It's because we have not equals as our alternative hypothesis. That made it a 2-tailed test. And so we're actually going to shade in both directions, right? So very good. When I calculate my p-value, I could use normal CDF. I'm going to double, actually. Let me do this. This will equal 2 times what I'll get in normal CDF for just one of these guys. So I'll do normal CDF. I'll do like, say, I'll focus on the positive. I'll do 3 to infinity. That says 3 to infinity, with a mean of 0 and a standard deviation of 1. Normal CDF. That would be 3 to infinity, 0, 1. And I got that. And I'll double it. And this comes out to being 0.0027 approximately. Now, actually, this So with this p-value, before I get a deeper thing, this p-value is definitely less than 10% significance, right? This is way smaller than 0.10. So I could say, since the p-value, which equals 0.0027, is less than alpha equals 0.10 or 0.10, right? That doesn't even look like a 1 anymore, but whatever. I reject the null hypothesis, right? We do have significant evidence that the true test average is not 85. We do have evidence that the true test average is not 85 because our p-value, very tiny, was less than our level of significance. Okay. Write in all caps helps. Okay, I'll try to write in all caps, Akira. You know me. I have many strengths and many faults, and neat handwriting is definitely not a strength of mine. Doreen, you ask a beautiful question. Why do we use z-scores? Can't we use that particular normal CDF? Doreen, you are correct. We absolutely could just use normal CDF the way that you described there. There's no reason that we would have to use the z-scores in order just to get the p-value. I'll tell you, though, in AP Stat, when we go through the process of doing a significance test, AP Stat has some quirks, and one of those quirks is next week we're going to see it's going to be required that you tell me the test statistic. It's just required. You're going to have to calculate it anyways. So I tend to just use the test statistic when I'm actually doing normal CDF because it's usually easier to type in. Cool. Now, just as an aside, I just wanted to point one small thing out. When we got this p-value of 0.0027 based on a z-score of 3, some of you might have been objecting in your heads, even if you didn't out loud. Well, do we really need to even use our calculator to figure out what that would be? Remember when we were memorizing stuff in the very beginning in chapter 2, when we were learning about normal distributions, we said that typically you go out 1, 2, 3 standard deviations on either side of the mean, 1, 2, 3, -1, -2, -3, to talk about a normal curve. And we said that between -3 and +3, 3 standard deviations from the mean, if we were to shade all that in, how much did I just shade in? What did I teach you way back in the day between -3 and +3 standard deviations of the mean? Someone type it in the chat. Nakira, Amy, giddy up, Anthony, giddy up, Josephine, giddy up. You guys are making me proud. The answer is 99.7%, right? And so we learned back in the day that should be approximately 99.7 from -3 to 3. Well, what did we just find for our p-value? We found that our p-value, which is actually the opposite of this, we saw was 0.0027, which if we rounded to just 3 decimal places would be 0.03, which was, oh my gosh, 0.9, if I did 1 minus 0.997. Oh, giddy up, right? So even if, and this is one of the reasons why it was so fun that the z-score, the test statistic came out to being exactly 3. One of the reasons it's so fun to me is because we didn't even need the calculator necessary to get this p-value. We could have just thought about what it would have been based on things we learned back in chapter 1. So, but there you go. Now, let's take a step back conceptually, right? We had the same set of hypotheses. Mu equals 85. Mu does not equal 85. And we used 2 different methods of evaluating these hypotheses. And the key here was that the result that we got for our 90% interval was consistent. It said that we should reject the null hypothesis as what we did when we did a significance test when alpha was 0.10. And in general, we will usually see that these things give you the same result. There was an example in the video very quickly that showed that that is not 100% the case, based on if we had sample standard deviations that varied from one another, or like we had in proportions when we used p-hat instead of p. But for the most part, it is equivalent to do a test on a hypothesis of not equal to. So a two-tailed test with either a confidence interval or with a significance test like this. If we did it, if we had actually just widened our confidence interval, say we did, let's make a different confidence interval. Let's say we had a 99% level of confidence. If we had used a 99% level of confidence here, say this became 99%, then what level of significance could we have used in the significance test? All right, someone tell me in the chat, 99% confidence, what's the level of significance for a significance test? 99%. Nakira chimes in quickly with 1%. Ostap, I'm sorry, it's not 5%. Nakira had it. 99% confidence would go down to alpha equals 0.01, a 1% level of significance. Now, the reason I point that out is that we should get consistent results there too. If I made a 99%, let's think for a second. Before I actually make the interval. When we got this p-value of 0.0027, was this less than alpha equals 0.01? Is this less than this? Answer, yes. So not only should I have rejected when alpha was 0.1, I should even reject this when alpha is 0.01. Now I'm telling you that should be consistent with the confidence interval. Let's do a 99% interval. This time I'll just do it in my calculator real quick. I'll do a Z interval, and I'm going to make my sigma 8. My mean was still 89. My sample size was 96. Let's make our level of confidence 0.99. And we got something that went from, if you see that, 85.56 to 92.434. Now, my friends, is 85 in that interval? Yes or no? You tell me in the chat. Is 85 in this interval? Answer, absolutely not. No. It's darn close. It's close to being in that interval, but it is not in the interval. So once again, even at a 99% level of confidence, or it's not in the interval, and therefore at a 1% level of significance, we're still going to continue to reject the null hypothesis, right? This ended up being very strong evidence against that the average is 85. Getting an 89 with 36 students, assuming the population standard deviation really is still 8, this is very, very strong evidence. We would reject the null hypothesis even at a 1% level of significance. All right. At least off the top of my head, I think I've sort of exhausted this particular example. Does anyone have any more questions? That I don't necessarily intend on stringing this out too long unless people have lots of questions. I know other people have things to do, and I don't want to just take up all your day. I know you've got other classes. So any other questions by anybody? I'll patiently wait here just for a minute. Amalia. Ooh, Amalia. No sad. No be sad. I hope you're having a good time, Amalia. Nakira, can I explain the level of significance, like the core idea of it? You absolutely got it. I will do that for you. Let me get another piece of paper. You know, maybe I should like auction off these pieces of paper at the end. You know, like I've been trying to save them and stuff. Like, I don't know, what are these going to be worth? You know, I don't know. Maybe we can raise some money for the math department, like real coronavirus memorabilia, the AP stat lessons with markers done by hand in a binder. I don't know. That's probably worth at least 25 cents. Dimitri, priceless. Oh man, you're too good. I am for the most part saving this stuff. So I'm not necessarily for money, but just to keep on hand here. But all right. So the concept of the level of significance. And when I say the level of Now I broke your rule. Nakira, you told me to write in all caps, and here I'm not doing it. The level of significance. There's a couple of ways of thinking about it. It's when we're talking about significance, I just want to look at the idea of significance. The idea is, with the level of significance, is I'm trying to decide, need a better marker here. Another thin one, what thick ones? Aha. I'm trying to decide is evidence significant, right? Just like in a criminal trial, I want to prove something beyond a reasonable doubt. You might be like, well, how strong does evidence have to be considered beyond a reasonable doubt, right? To make it really, 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 really significant evidence. Well, that's really what we're trying to do with a level of significance, right? Back when we were talking about significance, we said a result is significant if the difference, or if an effect differ. Oh my gosh, I can't even write. All right, all caps. If the difference or the effect is so large, it is unlikely to happen by chance. I don't know if that all caps is really all that much better, right? But if some type of effect is so large, it's unlikely to happen by chance. So the level of significance is going to be a boundary, right? It's a boundary for how unlikely something has to be, how unlikely a result must be to be significant, right? How unlikely will a result have to be considered really, really significant, right? So let's go back to the coin tossing thing, right? Let's say someone has, or actually we didn't do coin tossing, we were doing die throwing, but let's say someone has a coin, and if we looked at a coin, we would say the probability of someone flipping heads on the coin should be a half. The alternative should be that the probability, let's say that someone has a trick coin, they say they got a better chance of rolling heads than a normal die. So the probability they're saying is greater than a half of rolling heads. So P equals the probability of heads, right? Then a level of significance would be trying to say how unlikely will a result have to be so significant that I would reject the null hypothesis. Well, let's say someone flipped a coin. They did a flip 4 times, and they got 3 heads. And 4 times they got 3 heads. Is that going to be considered significant evidence to reject the null hypothesis? Now, in Akira, I'm with you. I agree. The answer for this should be no. That's why. It's not that hard to get 3 heads and 4 flips, right? And we could calculate this a bunch of ways. We could actually use a binomial to calculate this if we wanted. Let's ignore all the junk that we've been doing with significance tests. We could do a binomial, right? Where we said the number of trials is 4, right? P, what's the probability of flipping heads? Well, in the null hypothesis, it should be a half. And 3 is the number of heads we got. Oops, I just wrote plus. Go to. Heck, where'd that plus sign come from? All right. There's the probability that x equals 3, getting 3 heads out of 4, is 25% alone, right? And that's not even considering like the definition of a p-value of something like this, or even more extreme in the direction of the alternative. Technically speaking, I would have to add to this the probability of rolling 4 out of 4 based on the definition of a p-value. Boom, there's 4 out of 4, right? If I added to that the probability of 4 out of 4, the actual p-value for this scenario would be 31.25%, because that's the probability of getting this particular result or something more extreme. The p-value would be the probability that x is greater than or equal to 3, which will end up being 0.3125. So we would say this is not significant. Just obviously, it's not that hard to get 3 heads out of 4, and we could even calculate it. The probability was really high, 31.25%. So the p-value, the level of significance is just a formalized alpha that says how unlikely would a result have to be for us to reject the null hypothesis. Let's say I set it at 5%. In this case, we would fail to reject the null hypothesis because 31.25% is still way more than our boundary value of 5%. You have to be smaller than alpha to reject the null hypothesis, right? What if we had a result where instead of flipping 4 times, let's kick it up. Let's say we had done it 40 times and we got 30 heads. Would this be more significant or less significant in your mind than when we did 3 out of 4? 30 out of 40, is that more significant than 3 out of 4? Yeah, Vincent says it's more significant. Kira has a question. I'm going to read that, but other people, or Kira as well, answer the question, is 30 out of 40 more significant or less significant? So far, only Vincent's chimed in with more. Yes, this is, so 3 people, Vincent, Ostap, and Akira, all say it's more significant. Josephine, Doreen, kicking in. You're right, Nakira. It would be significant because there's more trials. And in more trials, it would be harder and harder and harder and harder and harder to get something different than what you expect. How many heads would you expect in 40 flips if it was fair? You'd expect 20. So getting something like 30 is going to be even harder to do when you had a larger number of trials, because you would expect things on average to be closer and closer. It's actually what the law of large numbers says, right? So the p-value for this scenario, getting 30 heads, would be like the probability that x is greater than or equal to 30, right? And to calculate this, I could actually use, let's go back to binomials. I could do binom CDF. Remember, binom CDF does everything to the left. So I could do 1 minus the probability that x is less than or equal to 29, right? And I could evaluate it that way. And I could say, okay, binom CDF. Binom CDF says 40 trials. The probability of success was 0.5, less than or equal to 29. I would do that. And then 1 minus that result. And binom CDF tells me my p-value would be 0.0011 about, right? So is this significant evidence now, getting 30 heads out of 40 flips? Heck to the yeah, 0.001 is way smaller than alpha is 0.05. And that is going to become significant for us. Why? Well, this is our boundary. Anything below this would have become significant. This ended up being way, 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 way below our boundary. And so there we go. Nakira, let's see here. Let's see. Hopefully that did. Nakira, did that help clarify level of significance for you in some ways? I mean, I ended up getting very mathy again, but that idea is it's just a boundary. How small of a probability does something have to be before you reject? And let me look at your question as well, too. So if we reject the null hypothesis, does that mean it's not significant enough to accept? Kira, I'm going to clarify something in your question. You said, if we reject the null hypothesis, right? If we reject the null hypothesis, that means it's not significant enough to accept. What do you mean accept? One thing that I'll say is accept the hoe. my friends, never, ever accept the hoe. That is verboten. Never accept the hoe. Cracking. Harry, you're back. I wonder what happened with Harkness. Never accept that. Sometimes we'll fail to reject. Fail to reject the null hypothesis. That's not the same thing as accepting it, right? Never accept it. Sometimes we'll just fail to reject it. So to go back to your question, Kira, you said, so if we reject the null hypothesis, so if we say reject HO, it says, does that mean there's not significant to accept? It means we do have significant evidence in favor of HA, right? When we say we reject the null hypothesis, we do have significant evidence in favor of HA. Let's look at the opposite, right? If I said fail to reject HO, that would mean we do not have significant evidence in favor of HA, right? But notice in both cases, we're talking about whether or not we have evidence for the alternative HA. We're always trying to collect evidence in favor of HA. We never collect evidence to prove the null hypothesis. We're never actually trying to prove the null hypothesis. We're only ever trying to prove the alternative. The null hypothesis is always an assumption. You don't prove your assumptions are true, you just make them, right? And so actually, this is just an interesting thing to think about in life when you think about what kind of assumptions you're making in the way you do things in the world. When you're making an assumption, you're not even subjecting it to proof. You're just assuming that it's the correct way of thinking about things. So if I just assumed that all of my students are cheaters, and I acted according to that principle in my life, then I wouldn't be trying to prove people are cheaters. I'm just assuming it and I'm making my choices based on it, right? Which would be a very sad thing to assume about my students. I tend to assume my students are not all cheaters, though I always leave open the possibility, maybe just a little bit. Maybe I think too highly of you. I don't know, you tell me. But our assumptions are problematic, right? So the assumptions we need to evaluate, right? And so in these cases, we're potentially going to reject an assumption by trying to find evidence against it. We're never trying to prove our assumption is true. We're trying to prove our assumption is in fact false. And that's really what we're doing here. So in the end of the day, when I fail to reject the null hypothesis, it doesn't mean that my assumption was true. It just means I didn't have enough evidence to disprove that assumption and prove the alternative. Let's see. Does that help, Kira, and all? Beautiful. Oh, yay. I helped multiple people. That makes me happy. Oh, all right. Any other questions? I'm waiting to see. All right. While I'm waiting to see if you have any more questions, your next assignment is going to be to look at types of error in significance tests, type 1 and type 2 error. And that gets tricky sometimes, especially trying to explain what a type 1 error and a type 2 error is when you're doing significance tests. So watch those videos. I hope they're helpful. And tomorrow I'm going to spend a lot of time talking about what a type 1 and a type 2 error are. And for those people that are struggling with this. Then Akira, you said, can you show the whole paper? the last one you worked on. So there's this one. Let's see here. There's this guy. Let me see if I'm going to zoom out a little bit, Kira, and see if that helps you get the whole thing. Actually, let me see if I'm going to move my phone. I have my phone on a tripod. Actually, see, there's the tripod. This is the setup, right? And that helps me do everything. But I'll try to make it go this way. Whoa, that didn't work. That really didn't work at all. All right, I'm going to stop. Undo. It didn't change the orientation of my video. It just changed the thing. So I'm going to zoom out and see if that helps. Kira, was this the paper you were talking about? Yes, and the one before. You got it for both. All right, so there's that whole paper. All right. There you go. Take a screenshot. You got it. Hopefully you can read that. And then the one before, there's this guy. And there's that. There's this guy too. You didn't have this guy. This one might be a little tougher to read. And I'll do one more. This guy as well. And there you guys go. All right. I think with that, I'll call it a day here. Let me go back to me mode. With that, I will call it a day. I will post a quick poll question asking people if it's impossible for them to be on the video, to be on at 11 a.m. or if you have conflicts. I suspect that the 30 or 35 people that were here today, obviously it is possible because you were here, but I will do another poll question just to see how many people really would that be a big problem for. And I might try to do a second one, but regardless, all of these are recorded. And so they'll be available online for you guys. Let's see here. I saw Timothy just joined us. I don't know if Timothy was here before, but now we're about to stop, Timothy. So I'm so sorry if you just joined us. Amalia, I got you. I am, you had a test, Timothy. I'm so sorry. Well, Timothy, no worries. You can just watch this video. And if you, I will be with you guys again. My pleasure. I'm so glad that we can still connect this way and have these lessons. I haven't started recording any videos for next week yet, but I think I might start doing that tomorrow. So we'll be ready to go. And actually I have to put a lot of work in my philosophy class, which I've been putting all my time for you guys. And because technically classes at Westchester don't start again until May 30th. They gave us 2 weeks to get everything together, but so I got to get working on them. But a link for philosophy. I'll if you guys want to dip into the philosophy classes, you can jump in. I'll share most of the videos that I'm going to have there. Some of them I actually created years ago, and I'm going to just keep the videos that are up online. But I will have some Zoom sessions as well too, and we'll see how those go. But anyways, you guys have a beautiful day. I am I'm about to shut down this thing. I'm going to turn the video off. Where's the video record button? And all right, video is just stopped recording.